I'm going to go to training model 9, which tells a bit more on how to run jobs. So still working with the scheduler. So here, what we want you to learn, and probably this is the most important module if you haven't used the supercomputers yet. So know the scheduler and create your own batch scripts. So you already saw that batch script, which has the information of the resources I needed for my job. So then having a script, submit it, monitor, and to cancel it. We haven't canceled it yet. Also, a very important part is to open an interactive session where you can work with the supercomputer through the command line directly in the compute nodes. That is super useful for development. Key resource requirements in a batch script. I guess the information that needs to be put always. And then finally run a program. So that's what we are going to do here. So a batch script. I already showed you quickly a script. So it's basically a script. You decide with which shell is going to interpret it. We usually use bash as the shell script. And then in that script, you have information for the scheduler to reserve your resources, but also the rest is just a normal bash script with a series of commands that needs to be executed for the job to run. Okay, so features in a batch script are the header with the sbatch that you already saw. So one best practice for improved reproducibility, specify resource requirements within the batch script rather than via command line. Writing resource requirements in the batch scripts is more reproducible for yourself, your research team, and the support staff. Basically, yeah, reproducibility is very important. It's super important, especially when you're in trouble and you don't know what happened. Yeah, if you don't use scripts to do your job, then who knows what you were doing yesterday or the minute just before when things were working and now they are done not working. So if you put everything in script, every single step, every definition you need, every environment variable you need, every model you need to load in the script, then you can basically reproduce. And if there is a problem, you can find it easily. Okay, sbatch and skew. So the idea is yeah, I think, okay. So there is a demo here that I need to do. Should be similar of what I did. So now it's in running jobs. Yeah. So again, cd running jobs. Okay. So what the demo is asking me is to submit the monitor script. So let's take a look first. Submit monitor. So that's the name. Submit monitor again is going to go to the work queue. Similar, just one task per node, and one CPU per task, so that only one core, only 1 minute to run. It's exactly the same script as before. It's basically the same script. Okay. So let's do it. Just submit monitor SQ me. Okay. So this one is not running yet. Submit monitor is not running yet. And submit monitor is now running. So first, it didn't know when it was going to run. Again, didn't know, but then the scheduler checked the queue, checked my job, and said, okay, there's space for you to run, and it sent it. And it sent it to the node 002792. The other job that I was forgetting that asked for a lot of resources is scheduled for tomorrow, and it's still there. So now, before I forget, I need to cancel it. So I need to use sbatch for submission, sinfo for checking the partitions, if you remember, sq for checking my own jobs, and then scancel for canceling my jobs. If they are either if they are running or they're just waiting in the queue for some allocation, you can cancel them. So I copy pasted the job ID of my job and it's cancel it. And then if I check what is in my own queue, there's nothing. So the first one finished because it was going to be just 1 minute, and the other one has been canceled. So now I don't have anything in the queue. Okay, so let's keep going here. Yeah, job output and canceling jobs. Okay, yeah. The job output, I haven't checked anything about it. And we did the canceling. So job output. So let's check. So usually you can tell the name uh, of the file where you want to store the output. That's another sbatch indication. But if you don't indicate anything, Slurm by default will put the output in files like this one. So Slurm dash the number of the job ID dot out. So if we check the content of that one, that is where you check if your job, or it's kind of a first check to check if your job ran successfully or as you desired. So these were the commands. Give me the time. And then there was a loop that was waiting for some seconds, asking for what is the host name, and then give me the time. So basically, in theory, okay. Yeah, so let's check again the script. Yeah, so this is a loop 2 times, waiting 15 seconds each time. Please echo what is the host name and what was the date. So the command date gives date and time at the same time. So that's the output we see in um, in that output file. And you see this is the name of the node. So it's not when you say host name. Remember, if I echo host name here, it's going to be the name of the login node. It's not a variable, is a command, hostname. Okay, so hostname is the name of the login node, Setonix01. And if you do hostname in a compute node, it's going to give you the name of the node. In this case, 002792. That's where the job was running. Okay, so does export change the device receive automatically or yeah, so yeah. So that question was for the prompt, isn't it? Yeah, I don't know about that. So exercise, hitting the time limit. Okay. Yeah, so this is just for you to check what are the kind of messages when a job is trying to keep running, but reaches the limit of the time available. So that job is the time limit job. Okay. So let's do it. Let's be AI time limit. Okay, so this job is named time limit. It's going to the work partition. Again, it's asking just for one core, and the limit is 1 minute. But in this case, rather than doing just 2 steps in this loop, it's going to try to do 8. And every time wait for 15 seconds. That is more than the minute. So it will not reach this final step. It will break somewhere here. And Slurm will give you a message about that. Okay, so batch time limit. SQ me. It's not running yet. Not running yet. So this is still Slurm processing it and thinking what it's going to do with that job. Okay, it's now running. Prolog is sort of the first stage of running. Now it is running and we will need to wait for a minute. So time left in the whole time, it was 49 seconds, but now 36 seconds and it's going to finish soon. "26 seconds. Mhm. 11 seconds left. 8 seconds. 5 seconds. I should have done something else, but anyway. Okay. Now it's doing the part of canceling it. At some point, it's going to be canceled. Still sort of running. Not running anymore. So yeah, I can now check the content of that other output file, which is the 6694. Okay, so it gave me the date, keep giving me the host name. Now it ran in another node. And then at some point it reached the time limit and you receive this message. So it says an error. I don't consider it really an error. It's just basically reaching the time limit. So what users should do is to plan. Usually what users do many times is to let it reach the time limit and save some checkpoints every certain number of uh, steps in the simulation. Sometimes it's very difficult to calculate the exact time your job is going to end. So you sort of do an estimate and set up your job to run close to the 24 hours, but sometimes, yeah, you miscalculate. But anyway, you should have some kind of regular checkpointing. Like for example, every hour of your job, do a checkpointing just to be safe. Because if you only have a checkpointing at the end and you miscalculate, then your job will be canceled before your code saves the data into the disk for restart, and then you will lose all your work during the done for by that job. There are some other common error messages like these are really errors. Like for example, this one segmentation fault. This is usually an error in the code. So the code is trying to do something wrong with the memory, uh, uh, like an invalid memory access, or sometimes trying to use more memory than the one that is available in the node. And these other errors out of memory, this is clearly an out of memory error. These are typical errors that you can find. So yeah, check the output file first. So there are enough messages there to know what may be happening with your job. That's the first check we always do, check those output output files. So what about if you want to know something about past jobs or some other information about the jobs that are running um, or in the queue? So there are two other commands, scontrol and sact, like saccount, to check for the history of the job. There is also another command of Slurm that is called SEFF, like efficiency, I think, that tells some more information about the job. In this case, how efficiently is it using the resources? So let's check what has happened. So there are many additional options of the sacct. You can check the documentation of Slurm itself to check the additional options, but with the plain sacct command, it gives you a list of previous jobs, how the some information about them. So for example, this one first job is the first one we tried. One thing is, if you remember, it was using all the time, it was one task, one CPU, but here it's saying allocated CPUs equals 2. This is a problem with Slurm information. And the thing is that the CPUs are allowed to have this thing of hyperthreading, but the Slurm considers each of the cores like 2 CPUs for their accounting. So it is weird when you see double numbers in in the in the allocated uh, CPUs. It is weird. So this one failed. This one is the one that we ask for 128, well, 1,000, like 10 nodes. And again, here it's appearing as a double number. That is not good. But anyway, you can check this job went to the work partition and completed. This one completed correctly. This one failed. This one was canceled. I canceled it. Another one's completed. This one reached the wall time. This one was timeout. And for DS control, we can do DS control show job, and then, for example, this one. Let's control invalid job ID. Okay. Yeah, the job needs to be running to do DS control. So let's submit. Time limit again, and then do the S control with 6978. Yeah, needs to be running or in the queue. So you can check more information about the job with this S control thing. You can check the submit time, the what is important. So here should be the node where it's going to run. Probably it's not running yet. Yeah. So the first one, it was not running yet. Now that it's running, it is running in node 2025. Number of nodes 1. And again here, the number of CPUs is being doubled by the scheduler in the information they are giving, and some other information about the script, the output file, etc. So this might be important just to check that you are getting the resources you are asking. Just bear in mind this doubling of the number of CPUs. Here's also how much memory is being allocated, etc. So more information about your job, more than what you get with the SQ. Okay. So the next part, which is important, is the SLOG session. So the SLOG session, let me put this big. Basically, is an interactive session in the compute nodes. So in order to go to a compute node with an SLOG session, let's ask for just one node. So remember the headers in the script files. You can do, well, let's say cut time limit. So remember there was the partition, the number of tasks per node, the number of CPUs per tasks, and the time. So all that can be given here to SLOG. So if you do SLOG and then you do partition work, number of tasks 1, and time. Let's go for a minute too. Then the scheduler finds a space, tells you if there is no space, keeps you waiting in this pending job allocation. But if it finds, gives you the resources, grants the allocation, and then sends you there. So it put us in the node 2024. So now, yeah, now we are in the compute node, and here, in theory, we should be executing code using the resources that we asked for. In this case, we only ask for one core just to demonstrate the salloc command. To exit salloc, you do exit. But for example, we can ask for number of nodes. You can check this in the documentation, but the number of nodes can be specified with -n. So let's ask for one node, and let's ask for all the node as an exclusive node. So now we're going to have 128 cores. Okay, it found a node. It has been granted, and we have 128 cores available. So if we do srun hostname, that command will be executed 128 times in a different CPU. So that's what we are going to see next. The srun command is very, very important, and this is the command in which we indicate to execute an executable. In this case, we are executing just the hostname, but as you can see, it ran 128 times, each time in a different core. So let's go for it. I'm out of the SLOC. So this is very important an interactive session for debugging, compiling, and executing your code, and keep testing before when you are developing a code. Okay. Yeah. So now the usual codes that are run in the supercomputer are codes that run in parallel. There are typically two paradigms or ways of programming for using resources in parallel. One is that uses MPI, which is a message passing interface that is used for multiple when we want multiple processes to execute at the same time, divide and conquer computational work. That's yeah, the idea is basically the codes are prepared to distribute a big chunk of work that needs to be done, a computation. The code is prepared to divide this work and distribute it to the many, in this case, tasks that are going to be run. That's for the MPI. So the OpenMP is another kind of parallelism. Okay, so distributed memory. The thing is that the memory, when you divide and conquer, the pieces can reside in the memory of each node or each core, but this memory is not shared by the other tasks. So the way you share the information is via the message passing interface. So that's the way you share information. In the case of using threading, you have a shared memory approach. So again, many cores available and do different things or pieces of the work, but the information is in the memory that is available by the many. In this case, we call them threads, OpenMP threads. So they can access the same memory. So you don't need to pass messages in between the threads. Problem is that this works fine in a single node level, but cannot work in multiple nodes. So for multiple nodes, when you need to execute your job in multiple nodes at the same time, you will always need to do some kind of MPI. Usually the codes use both at the same time. So they use MPI to communicate between nodes, but in the same node, the tasks that needs to be done by the same node can be done and programmed using OpenMP or shared memory. Use a combination of both. For the GPUs, yeah, the GPUs are a bit different. We are going to talk about them tomorrow. But the thing is, basically, these accelerators can execute a lot of computation very fast at the same time. So the thing is, programs are prepared to load the workload towards the GPU, and then the GPU executes the computation in parallel with with the multiple cores they have. Again, if you need to share information between two GPUs, you will need to use MPI to send information from one GPU to the other GPU, and if you need multiple GPU nodes, the same. It has a peculiar way of programming. Usually, these are the typical languages for programming on GPUs. HIP here in Cetonix, because we only have AMD GPUs. And for NVIDIA GPUs, the typical language is CUDA. And there's OpenMP can also be used for sending some kind of work to the GPU that is called target offloading. OpenACC and OpenCL do the same, target offloading.